Far from Earth, beyond the warmth of the sun, there are worlds that appear completely frozen. Their surfaces are locked in ice, cracked and motionless, reflecting only faint light from distant stars. For centuries, these moons were thought to be lifeless, cold remnants, circling giant planets in silence. But beneath that ice, something unexpected may exist. Not rock, not emptiness, but water. Vast, dark oceans, hidden far below the surface, moving slowly in total darkness. These oceans do not sparkle under sunlight, and they are never touched by wind or waves. They exist under immense pressure, sealed beneath kilometers of ice, warmed not by stars but by gravity itself. The idea is quiet, almost unsettling. Oceans without skies, water without weather, seas that have never seen a sunrise. And yet, by every scientific measure, these hidden oceans may be among the most stable environments in the solar system. In recent decades, space exploration has begun to reveal that moons like Europa, Enceladus, Ganymede, and Titan may each contain more liquid water than all of Earth's oceans combined. These discoveries have reshaped how scientists think about habitability, not just in our solar system, but throughout the universe. If oceans can exist without sunlight, then perhaps life does not need planets at all. Perhaps it only needs time, chemistry, and darkness. This documentary explores those hidden oceans. It moves slowly beneath the ice, following the physics that keeps water liquid in the coldest places, the biology that might survive without light, and the deep-sea parallels that connect these alien worlds to the most extreme environments on Earth. Along the way, we'll reflect on what it means for water to be common, for oceans to be hidden, and for life to exist far from everything we recognize as familiar. If you find value in calm, long-form science documentaries like this one, you're welcome to like the video or subscribe to the channel. It helps support future explorations into deep space, deep oceans, and the quiet questions that sit between science and philosophy. And now, we begin our descent not downward through Earth's seas, but inward, beneath the frozen surfaces of distant moons, toward oceans that have never known the Sunday. Worlds made of ice. From a distance, icy moons appear deceptively simple, pale spheres drifting through darkness, locked in slow orbits around giant planets. Their surfaces reflect faint sunlight, revealing little more than frozen plains and fractured crusts. For much of human history, these worlds were considered static and lifeless remnants of a colder, quieter region of the solar system, where geological activity had long since faded. Ice, after all, was assumed to be the final state, a signal that energy had run out. Yet the outer solar system is not as still as it appears. Beneath the frozen surfaces of these moons, motion persists. Time continues its slow work, and ice, rather than marking an end, becomes a boundary between two very different worlds, one visible, one hidden. The formation of icy moons was anything but gentle. In the early solar system, gravity drew material together in chaotic environments filled with collisions, heat, and instability. These moons formed alongside their parent planets, accumulating rock, metal, and water ice as they grew. As they cooled, heavier elements sank inward, while lighter materials formed outer layers. What emerged were not uniform spheres, but stratified worlds, layered by density and temperature. Over billions of years, those layers evolved. Ice thickened at the surface, shielding the interior from the vacuum of space. Beneath it, rock retained heat from formation and radioactive decay. More importantly, gravity never stopped acting. Each orbit around a massive planet subjected these moons to constant stretching and compression. They were pulled out of shape, then allowed to relax again, over and over, in a slow, rhythmic cycle that continues today. Europa offers one of the clearest examples of this process. Its surface is unusually smooth, marked by long, intersecting fractures that suggest a shell in motion. These cracks are not random. They trace the stresses imposed by Jupiter's gravity, bending Europa's icy crust like a sheet of metal repeatedly flexed. The ice responds not by shattering completely, but by deforming, healing, and fracturing again over time. Beneath that shell, scientists infer the presence of a global ocean, kept liquid by the friction generated during these tidal interactions. Enceladus, orbiting Saturn, presents an even more dramatic case. Despite its small size, it displays active geology. Near its south pole, enormous fissures known as tiger stripes vent water vapor and ice particles into space. These plumes are not remnants of an ancient past. They are happening now. Material from a subsurface ocean is being ejected directly into orbit, forming one of Saturn's rings. The Moon is losing mass, yet remains active, sustained by tidal heating that prevents its interior from freezing solid. Ganymede, the largest moon in the solar system, carries complexity on an even grander scale. Its size allows it to retain significant internal heat, and its strong magnetic field hints at a dynamic interior. Scientists believe Ganymede may host multiple subsurface oceans stacked between layers of ice and rock. These oceans are not open seas, but isolated reservoirs separated by different crystalline phases of ice formed under extreme pressure. In such an environment, water exists in unfamiliar forms, behaving in ways rarely seen on Earth. Titan, Saturn's largest moon, stands apart in yet another way. Its thick atmosphere obscures its surface, hiding a world where rivers and lakes flow not with water, but with liquid hydrocarbons. Methane and ethane rain from the sky, carving channels across frozen plains. Yet deep beneath this alien landscape, models suggest a water ocean may exist, insulated by layers of ice and organic material. Titan's chemistry is complex and slow, shaped by low temperatures and long timescales, offering a different vision of what an ocean world can be. What unites these moons is not their appearance, but their relationship with gravity. Tidal heating is a subtle but persistent source of energy. As moons orbit their planets, gravitational forces stretch them slightly when they are closer, then allow them to relax when farther away. This repeated deformation generates internal friction. Rock grinds against rock. Ice shifts and warms. Heat builds gradually, never erupting violently, but never dissipating entirely. Unlike geothermal activity on Earth, which is often localized and episodic, tidal heating is global and continuous. It does not depend on sunlight or atmospheric insulation. It relies solely on motion and mass. As long as a moon remains locked in orbit, energy continues to flow inward, quietly maintaining the conditions needed for liquid water beneath ice. Ice itself plays a critical role in this balance. Thick ice shells act as insulation, trapping heat below while shielding oceans from the cold of space. Under high pressure, ice behaves differently than it does on Earth's surface. It becomes stronger, denser, and capable of flowing slowly over geological time. Instead of cracking completely, it can deform like rock, sealing fractures and maintaining a stable barrier between ocean and vacuum. This creates a world sealed from above, where oceans are entirely removed from the rhythms of day and night. There are no tides driven by moons, no winds, no storms shaped by weather systems. Instead, movement is slow and internal. Currents are driven by heat gradients and chemical differences rather than sunlight. Time itself feels different in such environments, measured not in seasons but in millions of years. To understand icy moons, it becomes necessary to rethink what activity looks like. These are not worlds of eruption and spectacle, but of persistence. Their energy budgets are modest, their processes gradual. Yet over immense timescales, small amounts of heat become powerful. They keep water liquid. They allow chemistry to proceed. They create environments that may remain stable for longer than Earth's surface oceans ever could. Ice, then, is not merely a barrier. It is a stabilizer. It shields oceans from radiation, locks in pressure, and preserves conditions that might otherwise vanish. In doing so, it transforms these moons into some of the most intriguing environments in the solar system, not because they are dynamic on human timescales, but because they endure. Oceans without sunlight. On Earth, oceans are inseparable from the Sunday. Sunlight warms the surface, drives weather, and fuels the photosynthetic life that forms the base of nearly every marine food web. Even in the deepest trenches, far beyond the reach of light, the influence of the sun is still present, carried downward through falling organic matter and slow-moving currents. For most of scientific history, this connection seemed absolute. Where there was no sunlight, there could be no ocean in the true sense of the word, only frozen water or stagnant darkness. The icy moons of the outer solar system challenge that assumption completely. Their oceans, if they exist, have never known daylight. No sunrise has ever touched their surfaces. No seasons have ever passed overhead. These seas exist in permanent night, sealed beneath ice so thick that sunlight becomes irrelevant. And yet, by the laws of physics, liquid water may persist there for billions of years. To understand how an ocean can survive without sunlight, it helps to reconsider what sunlight actually provides. On Earth, its most important role is not simply warmth, but energy. Energy drives motion, chemistry, and biological activity. Remove the sun, and the surface freezes quickly. But energy can come from other sources, and in the case of icy moons, it arrives from within. Tidal heating acts as the primary engine. As moons orbit their massive planets, their interiors are slowly kneaded by gravity. This constant flexing generates heat, not enough to melt surfaces or create volcanoes visible from space, but enough to raise internal temperatures above the freezing point of water. Over time, even a small amount of heat, applied continuously, becomes significant. The result is a stable layer where ice melts into liquid, forming an ocean trapped between the frozen shell above and rock below. Pressure plays a crucial role in this process. Beneath kilometers of ice, pressure increases dramatically, altering the physical behavior of water. Under such conditions, water can remain liquid at temperatures well below what would normally cause freezing at the surface. Ice itself changes form, transitioning into denser, crystalline structures that sink rather than float. This creates a complex layering system where liquid water can exist stably between different phases of ice, insulated from the cold above and the vacuum beyond. In these environments, heat moves slowly. There are no rapid temperature swings, no daily cycles of warming and cooling. Everything changes on geological timescales. Currents, if they exist, are gentle and persistent, driven by subtle differences in temperature and composition. The ocean floor may be shaped by interaction with underlying rock, where heat and minerals seep upward into the water, creating chemical gradients rather than thermal extremes. This is where the absence of sunlight becomes less limiting than it first appears. Life, at its most fundamental level, does not require light. It requires energy and chemistry. On Earth, this fact was dramatically demonstrated in the late 20th century, when scientists discovered thriving ecosystems around hydrothermal vents on the deep ocean floor. These communities existed in complete darkness, sustained not by sunlight, but by chemical energy released from Earth's interior. At hydrothermal vents, seawater seeps into cracks in the ocean crust, becomes heated by magma below, and emerges rich in dissolved minerals. Microorganisms use these chemicals to fuel their metabolism through chemosynthesis, converting inorganic compounds into organic matter. Entire ecosystems grow around this process, independent of the Sunday. These discoveries forced a redefinition of habitability. revealing that life could flourish wherever energy and liquid water coexist. The oceans of icy moons may offer similar opportunities. Where water meets rock, chemical reactions occur, minerals dissolve, gases are released, and energy gradients form. Even without volcanic activity, slow interactions between water and a rocky mantle can generate hydrogen, methane, and other compounds that serve as potential energy sources. Over immense spans of time, these processes can accumulate, creating environments that are chemically rich, even if physically quiet. Darkness, in this context, is not an obstacle but a condition. In the absence of light, ecosystems, if they exist, would be shaped by entirely different constraints. Growth would be slow. Metabolism would be efficient. Life would not be driven by competition for sunlight, but by access to chemical gradients. Time itself would feel different, measured in slow cycles of change, rather than rapid bursts of productivity. These oceans would also be remarkably stable. Without surface weather, asteroid impacts, or climate fluctuations, conditions beneath the ice could remain relatively constant for millions, even billions of years. On Earth, stability is rare. Continents shift, climates oscillate, and mass extinctions reset biological progress. In contrast, an ocean sealed beneath ice may experience fewer disruptions, allowing evolutionary processes to unfold slowly and continuously. Yet this stability comes with constraints. Energy availability is limited. Nutrients must be recycled efficiently. Waste cannot be easily dispersed. Any life that emerges would need to operate within tight boundaries, maximizing every chemical reaction and conserving every available resource. Such conditions favor simplicity, resilience, and persistence over speed or complexity. From a philosophical perspective, these oceans invite a reconsideration of what it means for a world to be alive. They are not vibrant in the way Earth's surface appears vibrant. There are no colors, no landscapes shaped by light and shadow. And yet, beneath the ice, there may be motion, chemistry, and even biology unfolding quietly, unnoticed by the universe above. The idea of oceans without sunlight also changes how we think about the prevalence of habitable environments. If water can remain liquid without proximity to a star, then habitable zones expand dramatically. Moons, rogue planets, and distant worlds, once dismissed as frozen wastelands, may instead host hidden seas. The universe may be filled not with barren rocks, but with dark, water-rich interiors, waiting silently beneath ice. In this sense, icy moons blur the boundary between oceanography and astronomy. They are not simply objects to be observed through telescopes, but worlds that echo Earth's deepest environments. Their oceans resemble the abyssal depths more than any sunlit sea, defined by pressure, darkness, and chemical energy. Studying them becomes an exercise in connecting the familiar with the alien, using Earth's deep oceans as a lens through which to imagine life elsewhere. Pressure beneath the ice. Depth is not measured only by distance. It is measured by weight. As ice thickens above an ocean, its mass presses downward, layer upon layer, creating an environment where pressure becomes the dominant force shaping everything beneath it. In the hidden oceans of icy moons, pressure is not a secondary condition. It is the defining feature, quietly governing how water behaves, how chemistry unfolds, and how any form of life would need to exist. On Earth, pressure increases predictably with depth. Every 10 meters of seawater adds roughly one additional atmosphere of pressure. By the time the ocean floor is reached, organisms endure hundreds of times the pressure experienced at the surface. Yet even Earth's deepest trenches are shallow compared to what may exist beneath the ice of distant moons. There, oceans may lie beneath tens or even hundreds of kilometers of ice, creating pressures far beyond anything found on the seafloor of our own planet. This immense weight changes the nature of water itself. Under extreme pressure, water molecules pack closer together, altering density, viscosity, and freezing behavior. Ice no longer behaves as it does in a household freezer or a polar glacier. Instead, it transforms into unfamiliar crystalline structures known as high-pressure ice phases. These forms of ice are denser than liquid water, meaning they sink rather than float. As a result, an ocean can become trapped between layers of ice, sealed both above and below, isolated from the surface and the rocky interior alike. Such layered oceans challenge intuition. On Earth, ice floats, forming a protective lid that insulates water below. On icy moons, multiple layers of ice may exist, each responding differently to pressure and temperature. Liquid water may occupy a narrow band between these layers, circulating slowly, constrained by solid boundaries that shift and deform over geological time. The ocean is not an open basin, but a confined system, shaped by forces that act silently and continuously. Pressure also influences chemistry. Chemical reactions that would be slow or unlikely at Earth's surface can proceed differently under immense weight. Molecules are forced into closer proximity, altering reaction pathways and energy requirements. Gases dissolve more readily. Minerals behave differently. Even the pH of water can shift under pressure, changing how acids and bases interact. In such environments, chemistry becomes less familiar, governed by conditions rarely replicated in laboratories. For any life that might exist in these oceans, pressure would not be an occasional challenge. It would be constant, inescapable, and total. Every cell, every structure, every reaction would need to function under forces that compress and constrain. On Earth, deep-sea organisms offer a glimpse of what this adaptation looks like. Their proteins are structured to resist deformation. Their membranes remain flexible under compression. Their metabolisms are tuned to slow, efficient processes rather than rapid bursts of activity. But even Earth's deep-sea life may be only a partial guide. The pressures beneath icy moons could be several times greater, persisting without relief for billions of years. Evolution in such an environment would favor stability above all else. Change would be slow. Innovation would be incremental. Life, if present, would likely exist close to the limits of chemistry itself, operating at the edge of what molecules can sustain. Pressure also affects how heat moves through these oceans. Convection, the process by which warmer material rises and cooler material sinks, behaves differently under extreme conditions. Temperature gradients may be shallow, spreading heat evenly rather than creating strong currents. This results in oceans that are thermally stable, lacking the dynamic circulation patterns seen in Earth's surface seas. Movement exists, but it is subtle, measured in centimeters per year rather than meters per second. The sea floor of such an ocean, where water meets rock, becomes a region of particular interest. There, pressure is highest, but so is the potential for chemical interaction. Water-penetrating cracks in the rocky mantle can react with minerals, releasing hydrogen and other compounds. These reactions, driven by pressure and heat, create localized energy sources that persist even in the absence of sunlight. They are slow, steady, and long-lived qualities, well-suited to sustaining simple ecosystems over immense timescales. Yet access to these environments is uncertain. In some models, high-pressure ice layers may separate the ocean from the rocky mantle entirely, preventing direct contact. In others, pockets of liquid water may exist at the boundary, allowing limited interaction. The structure of each moon's interior depends on its size, composition, and thermal history. Small differences early in formation can lead to vastly different outcomes billions of years later. Pressure also shapes the ice above. Thick ice shells are not static. Under sufficient stress, they flow like rock, deforming gradually under their own weight. Cracks may open and close. Fractures may migrate. Over time, ice can recycle itself, sinking in some regions and rising in others. This slow movement helps regulate heat loss, maintaining a balance that keeps oceans liquid beneath. From a distance, these processes are invisible. Telescopes capture only frozen surfaces, smooth or fractured, marked by faint lines and subtle color variations. But beneath those surfaces, pressure is constantly at work, sculpting an environment far removed from the emptiness of space. It creates worlds where liquid water persists not because conditions are gentle, but because they are extreme in a way that favors stability. There is a quiet irony in this. Pressure, often seen as destructive, becomes a source of preservation. It locks water into place, shields it from radiation, and prevents rapid change. In doing so, it creates refuges dark, hidden, and enduring. These are not oceans of abundance, but of persistence. They do not change quickly, but they last. As we consider these environments, the idea of habitability becomes less about comfort and more about endurance. Life, if it arises beneath the ice, would not flourish in the way forests or coral reefs flourish. It would persist. It would adapt to constraints rather than overcome them. Its success would be measured not in diversity or speed, but in survival across unimaginable spans of time, where water meets rock. Beneath the immense weight of ice and water, at the deepest boundary of these hidden oceans, liquid finally encounters stone. This interface, where water meets rock, is one of the most important environments in planetary science. It is quiet, dark, and inaccessible, yet it is here that chemistry becomes active in ways that can reshape entire worlds. On icy moons, this boundary may be the primary source of energy, structure, and long-term change within oceans that have never known light. On Earth, the meeting of water and rock beneath the seafloor drives some of the planet's most fundamental processes. Seawater seeps into cracks in the oceanic crust, reacts with minerals, absorbs heat, and emerges altered. This slow circulation shapes ocean chemistry, regulates temperature, and supports ecosystems that exist independently of sunlight. These processes are not dramatic. They unfold gradually, governed by pressure, temperature, and time. And it is precisely this slowness that makes them so powerful. On icy moons, similar interactions may occur, though under conditions far more extreme. The rocky mantles of these moons formed early in the solar system, retaining heat from accretion and radioactive decay. Even after billions of years, some of that heat remains, trapped beneath insulating layers of ice and water. Where liquid water comes into contact with warm rock, chemical reactions begin, reactions that release energy, alter molecular structures, and create gradients that persist over geological timescales. One of the most important of these processes is known as serpentinization. When water interacts with certain types of rock rich in iron and magnesium, chemical reactions occur that produce hydrogen gas and heat. On Earth, serpentinization is a major driver of hydrothermal systems, particularly in regions where tectonic activity exposes fresh rock to seawater. These reactions can continue for millions of years, slowly transforming both water and stone. Hydrogen, once released, becomes a potent energy source. Microorganisms on Earth use hydrogen to fuel their metabolism, combining it with carbon dioxide to form organic compounds. This process does not require oxygen or sunlight. It relies entirely on chemical gradients created by water-rock interactions. In the deep ocean, entire ecosystems depend on this chemistry, forming stable communities in places once thought to be completely lifeless. If similar reactions occur beneath the oceans of icy moons, they could provide a steady, long-term energy supply. The key advantage of such systems is their durability. Unlike sunlight, which varies with distance and time, or volcanic activity, which can be episodic, water rock chemistry proceeds slowly and consistently as long as liquid water remains present. This creates an environment where change is gradual and predictable, favoring persistence over rapid growth. The nature of the rock itself matters greatly. The composition of a moon's interior determines which reactions are possible and how much energy they can produce. Some moons may have mantles rich in minerals that readily react with water, while others may be less chemically active. Small differences in formation history can lead to large differences in present-day habitability. A moon with the right mix of rock, water, and heat may sustain chemical activity for billions of years, while another may remain largely inert. Pressure further shapes these interactions. At great depths, water is forced into microscopic cracks and pores within rock, increasing the surface area available for reaction. High pressure also stabilizes certain chemical compounds that would break down at the surface, allowing complex molecules to persist. These conditions favor slow, efficient chemistry rather than rapid, high-energy reactions. Everything happens at a measured pace, unfolding quietly over time. In such environments, boundaries become blurred. The distinction between ocean and crust is not sharp. Water infiltrates rock. Rock dissolves into water. Minerals precipitate and reform. Over time, this exchange alters both phases, creating a dynamic interface that evolves slowly but continuously. It is here, in this zone of gradual transformation, that the potential for life is often considered greatest. Yet these environments are not uniform. Some regions may be warmer, more chemically active, or more permeable than others. Variations in heat flow, rock composition, and water circulation can create localized pockets where conditions differ subtly from the surrounding ocean. These gradients, small differences in temperature, chemistry, or pressure, are essential. Life, as understood on Earth, relies on gradients. It requires imbalance, something to exploit, however slight. In the deep oceans of Earth, life often clusters around such boundaries. Hydrothermal vents, cold seeps, and subduction zones all create conditions where water-rock interactions are intensified. These environments are not widespread, but they are persistent. They do not depend on the surface world. They exist independently, sustained by the planet's internal processes. In this sense, they are closer analogues to icy moon oceans than any sunlit sea. On icy moons, the scale of these interactions may be different, but the principles remain the same. Without plate tectonics as we know them, rock-water contact may be less dynamic, but not absent. Fractures created during formation, impacts, or internal stress can provide pathways for water to circulate. Over immense timescales, even limited interaction can produce significant chemical change. One of the most intriguing aspects of these environments is their stability. On Earth, hydrothermal systems are often transient, disrupted by tectonic shifts or changes in heat flow. Beneath icy moons, conditions may be far more constant. Ice shells dampen external disturbances. Orbits remain stable. Internal heat declines slowly. This allows water-rock chemistry to proceed uninterrupted for periods far longer than most Earth-based systems experience. Such stability has profound implications for the origin and persistence of life. Rather than emerging in brief windows of opportunity, life beneath icy moons, if it arises at all, may have had billions of years to develop, adapt, and refine itself. Evolution under these conditions would be slow, guided by small advantages and long-term survival rather than rapid expansion. The organisms imagined in such environments are not fast-growing or abundant. They would exist in low densities, spread thinly through vast volumes of water. Their metabolisms would be conservative, extracting as much energy as possible from limited resources. Waste would be recycled efficiently. Nothing would be wasted, because nothing could be. Even without life, these chemical processes matter. They influence ocean composition, pH, and the availability of dissolved gases. They shape the physical structure of the ocean floor and determine how heat is transferred upward. Over time, they may even influence surface features, subtly altering ice shells through heat flow and material exchange. From a scientific perspective, this boundary between water and rock is one of the most challenging to study. Direct observation remains beyond current technology. Instead, scientists rely on indirect evidence, magnetic fields, gravity measurements, surface chemistry, and plume analysis to infer what lies below. Each new mission adds another piece to the puzzle, refining models and narrowing possibilities. What emerges from these studies is a picture of oceans that are not isolated pools, but integrated parts of their worlds. They interact with rock below and ice above, participating in slow cycles of energy and matter. They are not static reservoirs, but living systems in a geological sense, even if biological life remains uncertain. The living shell of ice. Ice is often imagined as static and unchanging, a final state where motion ends. On Earth, frozen lakes and polar ice sheets appear solid and inert, responding only to seasonal shifts or slow glacial flow. But the ice that covers the oceans of distant moons exists under very different conditions. It is thicker, heavier, and shaped by forces that never fully release their grip. Far from being lifeless, this ice behaves more like a living shell, one that bends, fractures, heals, and slowly renews itself over immense spans of time. On icy moons, the ice shell is not a thin crust. In some cases, it may extend tens of kilometers deep, forming a vast barrier between the vacuum of space and the liquid ocean below. This thickness gives the ice mechanical strength, but it also allows it to flow. Under sufficient pressure, ice deforms not by breaking suddenly, but by creeping, molecule by molecule, responding to stress the way rock does deep within Earth's mantle. This slow movement transforms the ice into a dynamic structure rather than a rigid lid. Gravity plays a central role in shaping this motion. As moons orbit their planets, tidal forces continuously flex their interiors. The ice shell is stretched and compressed in rhythmic cycles, responding to gravitational pull that changes slightly over each orbit. This flexing generates heat within the ice itself, softening it and allowing movement to occur. Over time, stress accumulates and releases, creating fractures that can extend for hundreds of kilometers across the surface. These fractures are among the most visible features on moons like Europa. Long, dark lines crisscross the ice, intersecting and overlapping in complex patterns. They are not random scars. They record the history of stress within the shell, revealing how the moon has responded to gravitational forces over millions of years. Some fractures may penetrate deep into the ice, potentially connecting the surface with the ocean below, at least temporarily. When such connections form, material exchange becomes possible. Water from the ocean may rise upward, filling cracks before freezing again. Conversely, surface material ice, altered by radiation and micrometeorite impacts, may be carried downward. This slow cycling blurs the boundary between surface and ocean, allowing chemistry to mix across layers that might otherwise remain isolated. The ice shell also acts as an insulator. Its thickness traps heat within the interior, slowing the loss of energy to space. This insulation is crucial for maintaining liquid water beneath. Without it, internal heat would dissipate too quickly, and oceans would freeze solid. The ice shell, then, performs a balancing act, thick enough to preserve warmth, yet flexible enough to respond to internal forces. Temperature gradients within the ice further influence its behavior. Near the surface, ice is brittle and cold, prone to cracking under stress. Deeper down, where temperatures rise due to internal heat, ice becomes warmer and more ductile. This creates layered behavior within the shell, where different depths respond differently to the same forces. Stress may be absorbed gradually in warmer regions while being released suddenly near the surface. Over geological time, this layered structure allows the ice shell to renew itself. Old surface ice can sink as it warms and becomes denser, while fresher material rises from below. This process sometimes compared to plate tectonics on Earth, operates far more slowly and quietly. There are no continents colliding, no earthquakes felt across the surface. Instead, there is a gradual recycling that reshapes the shell from within. On Enceladus, this activity becomes visible in dramatic ways. The Moon's south polar region is marked by deep fractures from which plumes of water vapor and ice particles escape into space. These plumes suggest that, in some regions, the ice shell is thin enough or warm enough to allow ocean material to reach the surface directly. The escaping water freezes almost instantly, scattering into Saturn's orbit and forming part of its ring system. Such activity hints at a dynamic relationship between ice and ocean. The shell is not an impermeable barrier, but a semi-active membrane. It opens and closes pathways over time, regulating the exchange of heat and material. These processes may be episodic, turning on and off as orbital dynamics and internal heat flow change. Yet even intermittent connections could have profound implications for the chemistry of the ocean below. Radiation from surrounding space alters the ice at the surface, breaking molecules apart and creating new compounds. When this processed ice is transported downward, it carries oxidants and other reactive substances into the ocean. There, these materials can participate in chemical reactions that increase the available energy for any potential life. In this way, surface conditions, hostile though they may be, can indirectly enrich the hidden ocean rather than isolate it. The movement of ice also affects pressure within the ocean. As ice thickens or thins in different regions, the weight pressing down on the water changes. These variations may drive slow circulation within the ocean, redistributing heat and chemicals over time. The ocean is not static, but it is not turbulent either. Its motion reflects the slow breathing of the ice above, responding gently to shifts in mass and stress. From a distance, these moons appear unchanged, their surfaces frozen in place for eons. But the patterns etched into their ice tell a different story. They reveal a history of motion, adjustment, and renewal. Each fracture, ridge, and smooth plane is evidence that ice, under the right conditions, is not an end state, but a process. This living shell of ice shapes everything beneath it. It determines how heat escapes, how oceans remain liquid, and how isolated or connected those oceans may be to the surface. It influences the chemistry of the water, the availability of energy, and the potential for life to persist over long periods. In doing so, it becomes as important as the ocean itself in defining the character of these worlds. Understanding the behavior of this ice is essential for future exploration. Any attempt to reach the ocean below must pass through it, navigating a structure that is constantly responding to forces beyond human timescales. The ice is not simply something to be drilled through. It is a system to be understood, respected, and carefully approached. Slow currents in a lightless sea. Movement in an ocean is often imagined as something visible and immediate. Waves rise and fall. Currents sweep across vast distances. Storms churn the surface, redistributing heat and life in constant motion. On Earth, the sun and the atmosphere are the primary drivers of this activity. Wind transfers energy to water. Temperature differences create circulation. Even in the deep ocean, far below sunlight, motion is ultimately inherited from processes that begin at the surface. In the hidden oceans of icy moons, none of these familiar forces exist. There is no wind, no weather, no surface heating by sunlight, and yet, water does not remain perfectly still. Motion persists, slow and subtle, shaped by forces that act from within rather than above. These are oceans where currents move not in response to storms, but to gradients so faint they would be imperceptible on Earth's surface. The primary driver of circulation in these oceans is heat, not heat delivered suddenly or unevenly, but heat supplied gradually from below. As water near the ocean floor warms slightly due to contact with the rocky mantle or internal heat sources, its density changes. even small temperature differences can create buoyancy under immense pressure. Warmer water becomes marginally less dense and begins to rise, while cooler water sinks to take its place. This process, known as thermal convection, establishes circulation patterns that may persist for millions of years. However, convection beneath ice behaves differently than in open oceans. On Earth, warm water rising toward the surface eventually cools and sinks again, driven by contact with the atmosphere. In an icy moon ocean, rising water encounters an ice ceiling rather than air. The ice absorbs heat slowly, limiting the rate at which water can cool. As a result, convection may be weaker and more uniform, spreading heat gently, rather than creating strong vertical currents. Salinity also plays a role. Dissolved salts and other compounds affect water density, influencing how it moves under pressure. If chemical reactions at the ocean floor release salts or gases into the water, localized density differences can form. These gradients, though subtle, may be enough to drive horizontal circulation, slowly transporting material across the ocean's interior. Over long timescales, even minimal movement can result in significant redistribution of heat and chemistry. The shape of the ocean itself further influences circulation. Unlike Earth's oceans, which are shaped by continents and basins, subsurface oceans are enclosed between layers of ice and rock. Their geometry is defined by internal structure rather than surface features. Variations in ice thickness, heat flow, and rock composition can create regions where water moves differently, establishing slow currents that follow invisible pathways. Rotation adds another layer of complexity. As moons spin, the Coriolis effect influences fluid motion, deflecting currents and encouraging circular patterns. On Earth, this effect is responsible for large-scale gyres that dominate ocean circulation. Beneath ice, rotation may still shape movement, but on much slower timescales and with less energy. Currents may curve gently rather than forming strong, coherent systems. The result is an ocean defined by persistence rather than speed. Currents may take centuries or millennia to complete a single circuit. Heat and chemicals move slowly, but they do move, ensuring that the ocean does not become entirely stratified or stagnant. This slow mixing is crucial for maintaining habitability. Without circulation, nutrients would be depleted in some regions while accumulating in others, limiting the potential for sustained chemical activity. In Earth's deep ocean, slow currents play a similar role. The global conveyor belt, driven by differences in temperature and salinity, moves water around the planet over thousands of years. Though imperceptible on human timescales, this circulation regulates climate and distributes nutrients across vast distances. Beneath icy moons, analogous systems may exist, scaled to the unique conditions of pressure, darkness, and confinement. One of the most intriguing possibilities is the presence of boundary currents along the interface between water and ice. As heat from the ocean warms the ice above, melting may occur in localized regions, altering salinity and density near the boundary. This can drive horizontal flows along the underside of the ice shell, redistributing heat and influencing where the ice thins or thickens over time. Such interactions create feedback loops between ocean and ice, linking their evolution. At the ocean floor, currents may be shaped by topography. Even small variations in the rocky surface can redirect flow, creating zones where water lingers longer and chemistry becomes more active. These regions could serve as focal points for energy exchange, concentrating resources in an otherwise uniform environment. On Earth, similar effects occur around seamounts and ridges, where currents enhance biological productivity in the deep sea. Despite their importance, these currents would be nearly invisible to external observation. They do not create surface signatures easily detected by spacecraft. Instead, scientists infer their existence indirectly through measurements of magnetic fields, gravity anomalies, and surface deformation. Each piece of data offers a glimpse into the hidden motion beneath the ice, revealing an ocean that is active, though restrained. For any potential life, slow circulation presents both challenges and opportunities. Limited movement means limited access to new resources, favoring organisms that can endure long periods with minimal change. At the same time, circulation prevents complete isolation, allowing energy and nutrients to be shared across the ocean over long timescales. Life in such an environment would be shaped by patience, efficiency, and resilience rather than competition and speed. From a philosophical standpoint, these oceans invite a reconsideration of motion itself. Activity does not require intensity to be meaningful. In these hidden seas, the most important processes unfold so slowly that they escape immediate notice. Yet over billions of years, they shape entire worlds. Movement becomes something measured in geological time, reminding us that significance is not always tied to immediacy. Understanding circulation beneath ice also informs how these oceans might change in the future. As internal heat declines or orbital dynamics shift, circulation patterns may weaken or reorganize. Oceans could become more stratified or, conversely, more mixed. These changes would occur gradually, offering little warning but profound long-term consequences. Habitability, in this context, is not a fixed state, but a balance maintained over immense spans of time. Life without light. Life on Earth is so closely tied to sunlight that it is easy to mistake the two as inseparable. Plants, algae, and photosynthetic bacteria capture light and convert it into energy, forming the base of nearly every ecosystem at the surface. Even animals that live far below the waves ultimately depend on this process, feeding on organic matter that began its journey in sunlit waters. For much of scientific history, this connection shaped assumptions about life everywhere else. Where there was no light, it was believed there could be no living system of any significance. The discovery of life in Earth's deep ocean challenged that belief. At depths where sunlight cannot penetrate, ecosystems thrive around hydrothermal vents and cold seeps. These environments are not powered by light, but by chemistry. They revealed a different way for life to exist, one that depends on chemical energy released from the planet itself, rather than radiation from a star. This realization reshaped how scientists think about habitability, opening the door to the possibility that life could exist in places once considered permanently dark and inert. The hidden oceans of icy moons exist in darkness far deeper and more complete than any found on Earth. These seas have never been illuminated. They are sealed beneath ice that blocks even the faintest trace of starlight. If life exists there, it must operate entirely without visual cues, photosynthesis, or surface-driven cycles. Its existence would be shaped by a world where darkness is not an absence, but a constant. In such an environment, energy becomes the central constraint. Without sunlight, life must rely on chemical gradients, differences in concentration, temperature, or electrical charge that can be exploited to drive metabolism. On Earth, chemosynthetic organisms use reactions involving hydrogen, methane, sulfur, and iron to fuel their growth. These processes are slow and efficient, producing far less energy than photosynthesis, but they are reliable. As long as water and rock continue to interact, chemical energy remains available. In the oceans beneath icy moons, similar reactions may occur. Water, interacting with a rocky mantle, can release hydrogen and other reduced compounds. These substances, when combined with oxidants introduced from the ice above or produced internally, create energy gradients capable of sustaining microbial life. The scale of these gradients may be small, but over immense volumes and long timescales, they can support persistent ecosystems. Life in such conditions would likely be microscopic. Large, complex organisms require abundant energy to sustain movement, growth, and reproduction. In energy-limited environments, simplicity becomes an advantage. Microorganisms can survive on minimal resources, reproduce slowly, and persist in stable conditions for long periods. Their metabolisms can be finely tuned to specific reactions, extracting every possible unit of energy from their surroundings. Earth's deep biosphere offers an instructive comparison. Beneath the ocean floor and within Earth's crust, vast communities of microorganisms exist, living on timescales far removed from surface life. Some divide only once every hundreds or thousands of years. Their activity is so slow that it barely registers by human standards, yet collectively, they represent a significant fraction of Earth's total biomass. These organisms demonstrate that life does not require rapid growth or constant change to endure. In the oceans of icy moons, life may exist in a similar state of quiet persistence. Cells may remain dormant for long periods, activating only when conditions allow. Metabolic rates may be extremely low, conserving energy and minimizing waste. Evolution in such an environment would proceed slowly, guided by survival rather than competition. Natural selection would favor stability, efficiency, and resistance to environmental stress. Darkness also shapes perception. Without light, vision becomes irrelevant. Organisms would not evolve eyes or pigmentation. Instead, they might rely on chemical sensing, detecting gradients in temperature, acidity, or nutrient concentration. Communication, if it exists, would be chemical rather than visual or auditory. The sensory world of such life would be fundamentally different from anything experienced at Earth's surface. The absence of light also eliminates day-night cycles and seasonal rhythms. Time, in these oceans, is not marked by external cues. Biological processes would be regulated internally or by slow environmental changes driven by heat flow and chemical availability. Circadian rhythms, so common on Earth, may have no counterpart here. Life would exist in a continuous present, shaped by gradual shifts rather than repeating cycles. One of the most intriguing questions is whether complex life could ever arise in such environments. On Earth, complexity is often associated with energy abundance. Larger organisms, nervous systems, and active behaviors require sustained power. In the hidden oceans of icy moons, energy is scarce and diffuse. This suggests that if life exists, it is more likely to resemble Earth's simplest forms rather than its most elaborate. However, complexity does not have a single definition. Complexity can also arise through chemical diversity and long-term stability. Given billions of years, even slow processes can produce intricate systems. Molecules can accumulate, interact, and organize in unexpected ways. Life beneath ice may not mirror terrestrial complexity, but it could achieve forms of organization unfamiliar to us, shaped by constraints that have no equivalent on Earth's surface. The question of origin is equally profound. How would life begin in such an environment? On Earth, hypotheses about the origin of life often involve shallow waters, fluctuating conditions, and exposure to sunlight or atmospheric chemistry. Beneath ice, conditions are more constant. While this stability may limit certain pathways, it also provides protection. Once complex molecules form, they are shielded from radiation and catastrophic disruption, allowing them to persist and interact over long periods. Chemical reactions at the water-rock interface could create environments rich in the building blocks of life. Gradients in temperature and chemistry provide natural laboratories where molecules concentrate and react. Over immense timescales, these processes could give rise to self-sustaining systems. Whether this has happened remains unknown, but the possibility alone reshapes how scientists think about life's potential reach. From a broader perspective, life without light challenges human intuition. It suggests that life is not inherently tied to the visible, the warm, or the familiar. Instead, it may be a natural outcome of chemistry, wherever conditions allow. In this view, life is less an exception and more a tendency, a quiet expression of matter organizing itself over time. The hidden oceans of icy moons thus become more than scientific curiosities. They are tests of our assumptions. They ask whether life requires Earth-like conditions, or whether it can emerge in darkness, under pressure, sustained by minimal energy. They suggest that the universe may host forms of life that are not dramatic or abundant, but subtle and enduring. Even if these oceans are lifeless, their existence still matters. They demonstrate that liquid water, a key ingredient for life as we understand it, can persist in places once dismissed as frozen and dead. They expand the definition of habitable environments and hint that oceans may be more common in the universe than planets with open skies. As exploration continues, future missions may attempt to sample plumes, analyze surface chemistry, or measure subtle signals that betray biological activity below. These efforts will proceed cautiously, guided by an awareness of how fragile and isolated these environments may be. The goal is not conquest, but understanding, a universe filled with hidden water. When people imagine water in the universe, they often picture blue planets with clouds, oceans reflecting sunlight, and atmospheres shaped by weather. This image is deeply influenced by Earth, where water is visible, abundant, and dynamic at the surface. For a long time, this vision shaped how scientists searched for habitable worlds. Planets were prioritized, moons were secondary, water was expected to exist where starlight was strong enough to keep it liquid. The study of icy moons has quietly overturned that perspective. It suggests that water does not need to sit beneath open skies to endure. It does not need warmth from a nearby star, or even a planet to call home. Instead, water can hide sealed beneath ice, insulated by pressure, sustained by internal energy. In this view, the universe may not be dominated by dry, barren worlds punctuated by rare blue planets. It may instead be filled with dark, water-rich interiors, invisible to distant observation. Within our own solar system, icy moons already outnumber Earth-like planets. Jupiter and Saturn alone host dozens of moons, many of which contain large quantities of ice. Even if only a small fraction of these bodies harbor subsurface oceans, the total volume of liquid water beyond Earth could be immense. Europa and Ganymede are each thought to contain more water than all of Earth's oceans combined. When considered together, these hidden seas reshape the balance of water in our cosmic neighborhood. Beyond the gas giants, similar bodies may exist around other stars. Planet formation models suggest that icy worlds are common in the colder regions of planetary systems. Many of these objects never migrate inward. They remain distant, cold, and difficult to detect. Yet within them, internal heat and pressure may preserve liquid water for billions of years. These worlds would be invisible to most telescopes, their oceans concealed beneath thick shells of ice. The implications are profound. If water can persist in darkness, then the traditional concept of a habitable zone becomes incomplete. Habitability is no longer confined to a narrow ring around a star. It expands outward, following gravity, pressure, and time rather than light. Moons, rogue planets, and even free-floating objects ejected from their systems could host hidden oceans, warmed by radioactive decay or tidal interactions with unseen companions. This idea reframes the search for life. Instead of asking where sunlight is sufficient, scientists begin to ask where water can remain liquid over long timescales. Stability becomes as important as warmth. Isolation becomes a feature rather than a flaw. Worlds that experience fewer disruptions may offer environments where chemistry can proceed uninterrupted for immense periods, increasing the likelihood of complex outcomes. The deep ocean analogy becomes especially powerful here. Earth's abyssal plains are not the most productive environments, but they are among the most stable. They change slowly, buffered from surface chaos. Life there persists through extremes, adapted to constancy rather than abundance. Hidden oceans on icy moons may represent a similar class of environments on a cosmic scale. places where life, if it arises, is shielded from stellar violence, radiation, and catastrophic impacts. Even without life, these oceans matter. Water is a key player in planetary evolution. It influences internal dynamics, heat transfer, and chemical differentiation. The presence of liquid water beneath ice affects how moons respond to gravitational forces, how their surfaces evolve, and how they interact with their surroundings. In some cases, material from these oceans may even escape into space, carrying chemical signatures that can be detected remotely. Such signatures offer rare opportunities. When plumes erupt from Enceladus, or material from Europa's surface is altered by ocean chemistry below, scientists gain indirect access to environments otherwise unreachable. These moments are fleeting, but they allow glimpses into the composition of hidden seas, revealing salts, organic molecules, and hints of chemical processes occurring far beneath the ice. As detection methods improve, astronomers may begin to identify similar signatures around distant stars. Subtle variations in a moon's motion, unexpected magnetic interactions, or unusual surface chemistry could all point to subsurface oceans. Each detection would add to a growing realization that water-rich worlds are not rare exceptions, but common outcomes of planetary formation. This abundance of hidden water also invites philosophical reflection. Humanity's long association with oceans is rooted in visibility. We sail them, map them, and watch their surfaces respond to the sky. Hidden oceans, by contrast, exist without witnesses. They do not reflect starlight. They do not shape climates or coastlines. Their presence is inferred rather than observed, reminding us that much of reality operates beyond immediate perception. There is a quiet humility in this realization. It suggests that the universe may host countless environments as rich and complex as Earth's oceans, yet entirely unknown. These worlds exist not to be seen, but simply to be. Their significance does not depend on observation. They persist regardless of whether they are ever explored or understood. As science continues to uncover these hidden waters, the boundary between oceanography and astronomy continues to blur. Studying distant moons becomes an extension of studying Earth's own depths. The same principles, pressure, chemistry, energy flow, apply across vast differences in scale and location. In this way, the hidden oceans of icy moons connect the most remote regions of space to the deepest parts of our own planet, reaching oceans we cannot see. Exploring an ocean hidden beneath kilometers of ice is unlike any challenge humanity has faced before. On Earth, even the deepest seas remain accessible in principle. Submersibles descend through open water. Sensors are lowered from ships. Light, though absent at depth, is replaced by technology. Beneath the ice of distant moons, none of these assumptions apply. There is no open ocean to descend into, no atmosphere to support flight, and no surface that offers easy access. Every path inward must pass through a barrier shaped by pressure, cold, and time. The difficulty begins with distance. These moons orbit far from Earth, separated by hundreds of millions or even billions of kilometers. Any mission must operate autonomously for years, surviving radiation, extreme cold, and the limitations of communication delayed by vast distances. Once a spacecraft arrives, it must do more than observe. It must interact, measure, and infer the invisible. Initial exploration focuses on what can be sensed from above. Orbiters measure subtle variations in gravity, revealing how mass is distributed beneath the surface. Magnetometers detect faint magnetic fields generated as salty oceans interact with their parent planet's magnetic environment. Cameras map fractures and surface features, offering clues about ice thickness and internal activity. Each measurement is indirect, yet together they form a picture of what lies below. Landing on the surface introduces new challenges. The ice is not smooth or uniform. It may be brittle in some regions, fractured in others, and constantly stressed by tidal forces. Temperatures plunge far below anything experienced on Earth's polar ice sheets. Radiation from surrounding space alters surface chemistry, degrading materials over time. Any lander must endure these conditions long enough to conduct meaningful science. The greatest obstacle, however, lies beneath the surface. Drilling through kilometers of ice is not simply a matter of power. The ice may move, crack, or refreeze around equipment. Heat introduced to melt a path downward risks destabilizing the surrounding structure. Mechanical drilling faces wear, jamming, and extreme resistance. Even on Earth, drilling through thick ice sheets is a complex endeavor. On another world, it becomes an unprecedented challenge. To address this, scientists imagine new tools designed specifically for ice-covered oceans. One concept involves melting probes that descend slowly, using heat to sink through the ice while leaving behind a refrozen tunnel. These probes would carry instruments capable of analyzing ice chemistry as they move, transmitting data back to the surface. The descent would be measured in months or years, reflecting the slow pace required to navigate such an environment safely. Once the ocean is reached, the challenges continue. A probe entering liquid water beneath ice would encounter pressures far exceeding those faced by Earth's deep-sea vehicles. Communication with the surface would be limited or indirect, relying on cables or acoustic signals that must travel through ice and water. Navigation would be difficult without familiar reference points. Every movement would need to be cautious, deliberate, and efficient. Despite these obstacles, the potential rewards are immense. Direct sampling of an alien ocean would allow scientists to test hypotheses that have remained theoretical for decades. The chemistry of the water could reveal whether energy sources are present. Organic molecules could indicate complex chemical processes. Even the absence of life would provide critical insight, helping refine our understanding of where biology can and cannot arise. Ethical considerations also come into play. These environments, isolated for billions of years, may be pristine. Introducing Earth-based microbes could irreversibly alter them. Planetary protection becomes more than a procedural requirement. It becomes a philosophical responsibility. Exploration must balance curiosity with caution, ensuring that the act of discovery does not compromise what is being studied. In many ways, this challenge mirrors humanity's earliest ocean exploration on Earth. Early explorers ventured into unknown waters with limited tools, guided by indirect signs and careful inference. They moved slowly, learning as they went. The exploration of hidden oceans beyond Earth demands a similar mindset, one that values patience over speed, understanding over spectacle. Technological progress continues quietly. Advances in robotics, materials science, and energy efficiency bring these concepts closer to reality. Missions planned for the coming decades aim to refine measurements, identify promising regions, and test technologies that may one day pierce the ice. Each step is incremental, building toward a future where direct exploration becomes possible. Yet even without direct access, these oceans are already shaping how humanity understands the universe. They remind us that the most important environments may be those we cannot easily see. They challenge the assumption that exploration must always involve direct observation. Sometimes, understanding emerges from careful interpretation, from reading subtle signals and constructing models that respect uncertainty. The act of reaching these oceans, whether physically or intellectually, becomes a reflection of human curiosity itself. It is not driven by immediate utility or conquest, but by a desire to know what exists beyond familiar boundaries. The hidden oceans of icy moons invite us to expand our sense of place, to consider that life and complexity may thrive in forms and locations that resist easy discovery. As we look ahead, it becomes clear that these oceans will remain hidden for some time. Their exploration will be slow, cautious, and deliberate. But their influence is already felt. reshaping scientific priorities and philosophical perspectives alike. They serve as quiet reminders that the universe is deeper than it appears, and that some of its most important stories unfold far from light. Oceans, solitude, and the shape of existence. Hidden oceans invite a particular kind of reflection. They are not dramatic worlds marked by storms, continents, or skies. They do not announce themselves through light or motion. Instead, they exist quietly, sealed beneath layers of ice, shaped by forces that operate far beyond human timescales. To think about them is to confront a form of solitude that is both physical and philosophical, a solitude defined not by emptiness, but by isolation. On Earth, oceans are rarely alone. They interact constantly with the atmosphere, the land, and living systems at the surface. Their boundaries are porous, their rhythms tied to winds, tides, and seasons. Even the deepest waters are influenced by events far above. In contrast, the oceans of icy moons are removed from such interactions. They are cut off from the sky entirely, enclosed within their worlds, existing without reference to stars or sunlight. This isolation changes how we think about what it means for an environment to exist. These oceans do not support climates or ecosystems that shape a planet's appearance. They do not create coastlines or weather patterns. Their presence is internal, almost private, known only through indirect evidence and careful inference. They challenge the assumption that environments must be visible to be significant. If life exists in these hidden seas, it would experience isolation unlike anything on Earth. Entire biospheres would be sealed away from the rest of the universe, evolving without external input. There would be no exchange of material with space beyond rare, accidental events. No meteorites delivering new chemistry. No changing sunlight to drive adaptation. Life would be shaped almost entirely by internal conditions, responding to slow changes in heat, pressure, and chemistry. Such isolation raises questions about evolution itself. On Earth, life evolves in response to fluctuating environments. Climate shifts, geological upheaval, and mass extinctions periodically reset the course of biological history. Beneath ice, these disruptions may be rare or absent. Evolution would proceed without dramatic interruptions, guided by gradual selection rather than sudden change. Over immense spans of time, this could produce forms of life that are highly specialized, finely tuned to their environment, and remarkably stable. This stability is both a gift and a constraint. It allows complexity to develop slowly, protected from catastrophe. At the same time, it limits opportunity. Without external disturbances, evolutionary pathways may be narrow, favoring persistence over diversification. Life, if present, might reach an equilibrium and remain there, changing only as the planet itself slowly cools or its orbit evolves. From a human perspective, these oceans force a reconsideration of loneliness in the universe. Much of the search for life has focused on communication signals, atmospheres, or surface features that can be detected across space. Hidden oceans offer none of these. Even if life is abundant within them, it may never announce its presence. It may remain forever silent, existing without observation, communication, or recognition. This silence does not imply insignificance. In fact, it suggests that the universe may be richer than it appears, filled with processes and possibilities that unfold independently of observers. Hidden oceans remind us that existence does not require acknowledgement. Worlds can be active, complex, and meaningful, even if they remain unseen. There is a parallel here with Earth's own deep ocean. For most of human history, the abyss was unknown. Entire ecosystems existed beyond reach, shaping global processes without ever being witnessed. Only recently have we begun to understand their role. Even now, much of Earth's deep biosphere remains unexplored, its inhabitants living and dying without ever being observed. In this sense, icy moon oceans extend a familiar pattern outward into space. They suggest that nature does not prioritize accessibility. It creates environments according to physical laws, not human curiosity. If those environments are hidden, they remain hidden. Discovery becomes an act of patience rather than inevitability. These ideas also influence how humanity sees itself. If life can exist in isolation, sustained by minimal energy and slow processes, then life is not a rare accident dependent on ideal conditions. It becomes a resilient phenomenon, capable of persisting wherever circumstances allow. This perspective shifts humanity from the center of the story to one example among many possible outcomes. At the same time, hidden oceans highlight the fragility of connection. Life beneath ice may be abundant in its own way, yet entirely disconnected from the broader universe. It may never know that stars exist, or that other worlds host oceans under open skies. Its reality would be complete within its confines, defined by water, rock, and chemical gradients rather than cosmic context. This raises questions about intelligence and awareness. If intelligent life were to arise in such an environment, how would it perceive reality? Without light, without a sky, without distant objects to observe, its understanding of the universe would be profoundly different. Knowledge would be local, experiential, and limited to what could be sensed directly. The broader cosmos might remain entirely unknown. While such speculation extends beyond current science, it underscores the philosophical impact of hidden oceans. They invite contemplation not just of where life might exist, but of how existence itself can be shaped by environment. They suggest that consciousness, if it arises elsewhere, may be shaped by conditions so different from ours that comparison becomes difficult. Even without life, these oceans challenge human-centered narratives of significance. They exist regardless of whether they are explored, regardless of whether they ever host biology. Their presence alters planetary dynamics, influences orbital interactions, and reshapes our understanding of water in the universe. They matter because they exist, not because they are useful or observable. As scientific understanding deepens, the realization grows that the universe is not optimized for visibility. Many of its most important processes occur in darkness, shielded from direct observation. Nuclear fusion happens inside stars, hidden beneath glowing surfaces. Planetary formation unfolds within dust clouds. Biological activity thrives in Earth's subsurface. Hidden oceans fit this pattern, representing another layer of reality, operating beyond immediate perception. This recognition encourages humility. It reminds us that what we see is only a fraction of what exists. The visible universe, rich as it is, may be a thin surface layer covering deeper, quieter processes. Oceans beneath ice become symbols of this idea, vast, active, and unseen. As we approach the final chapters of this documentary, the focus shifts inward rather than outward. The question becomes not only what these oceans reveal about the universe, but what they reveal about how humans search for meaning. In seeking hidden oceans, we practice a kind of curiosity that accepts uncertainty, values patience, and respects the unknown. Earth's deep ocean as a mirror. Long before humanity imagined oceans beneath distant moons, Earth itself held a similar mystery. For centuries, the deep ocean was an abstraction, an unknowable depth beneath the surface, assumed to be empty, cold, and inert. Early explorers believed that life could not exist beyond a certain depth, that pressure and darkness would make survival impossible. This belief was not born of evidence, but of limitation. The tools to look deeper simply did not exist. When technology finally allowed humans to descend into the abyss, the assumptions collapsed. Life was not only present, but persistent. Strange organisms thrived under crushing pressure, in temperatures near freezing, sustained without sunlight. Entire ecosystems existed far below the reach of waves and weather, shaped by chemical energy rather than light. The deep ocean revealed itself not as a dead end, but as a parallel world, quiet, slow, and resilient. This revelation reshaped biology, geology, and oceanography. It also provided a template for understanding environments beyond Earth. The conditions found beneath Earth's oceans, darkness, pressure, energy, scarcity, isolation, closely resemble those predicted beneath the ice of distant moons. In many ways, Earth's deep sea is the closest analog humanity has to those alien oceans. At hydrothermal vents along Earth's mid-ocean ridges, water heated by magma rises from the seafloor, carrying dissolved minerals and gases. Around these vents, life flourishes without sunlight, powered by chemosynthesis. Tubeworms, clams, and microbial communities form stable ecosystems that may persist for thousands of years. These environments are not widespread, but they are enduring, sustained by slow geological processes rather than surface conditions. Cold seeps offer another comparison. Here, hydrocarbons and other compounds leak from the seafloor, providing energy sources for microbial life. Like hydrothermal vents, these systems operate independently of the sunday. They demonstrate that life can exploit chemical gradients wherever they arise, even in environments that appear hostile by surface standards. Beyond these dramatic sights, much of Earth's deep biosphere exists quietly within sediments and rock. Microorganisms inhabit pores and fractures kilometers below the seafloor, living at metabolic rates so slow they challenge traditional definitions of life. Some may survive on energy released from radioactive decay or chemical reactions that occur only intermittently. Their existence shows that life can persist at the very margins of energy availability. These discoveries are crucial for understanding icy moons. They reveal that life does not require abundance, speed, or complexity to endure. It requires stability, water, and a reliable energy source, however modest. Earth's deep ocean teaches that isolation is not necessarily a barrier to life, and that darkness does not preclude biological activity. The parallels extend beyond biology. The physical behavior of water under pressure, the formation of high-pressure ice phases, and the slow circulation of deep currents all find counterparts in Earth's oceans. Studying these processes on Earth allows scientists to refine models of subsurface oceans elsewhere, translating familiar principles into unfamiliar contexts. Yet important differences remain. Earth's deep ocean is still connected, however indirectly, to the surface world. Organic matter sinks from above, delivering energy and nutrients. Tectonic activity reshapes the seafloor, creating new habitats and destroying old ones. Climate changes influence circulation patterns over time. Beneath icy moons, such connections may be weaker or absent altogether. This distinction highlights the uniqueness of hidden oceans beyond Earth. They represent environments even more isolated than Earth's abyss, more stable, and potentially more enduring. While Earth's deep sea changes over millions of years, subsurface oceans on icy moons may persist in near equilibrium for far longer, protected by thick ice shells and insulated from external disruption. Studying Earth's deep ocean also underscores the importance of patience in exploration. Many of the most significant discoveries came not from brief visits, but from sustained observation. Instruments left on the seafloor for years revealed slow processes, invisible in short-term studies. Similarly, understanding hidden oceans beyond Earth will require long-term missions and a willingness to accept gradual progress. There is also a philosophical lesson embedded in this comparison. Earth's deep ocean reminds us that the most important aspects of a system may lie beneath the surface, unseen but influential. The visible world is often shaped by processes that operate out of sight. Hidden oceans extend this lesson into space, suggesting that the universe's most significant environments may be those least accessible to observation. As technology advances, Earth's deep ocean continues to serve as both a laboratory and a training ground. Autonomous vehicles, long-duration sensors, and pressure-resistant materials developed for deep-sea exploration inform the design of future missions to icy moons. In this way, exploration of our own planet becomes preparation for exploration beyond it. The mirror between Earth's deep sea and alien oceans is not perfect, but it is instructive. It shows how understanding one environment can illuminate another, even across vast distances. It also reminds us that discovery often begins close to home, in places once overlooked or misunderstood. Rethinking rarity in a quiet universe. For much of modern history, humanity has lived with the idea that worlds like Earth are rare. Liquid water, stable environments, and long-lasting conditions suitable for life were thought to require a precise balance of distance, mass, and energy. This belief shaped both scientific inquiry and philosophical reflection. Earth appeared as an exception, a narrow oasis in an otherwise hostile cosmos, defined by coincidence and fine-tuning. The growing understanding of hidden oceans quietly erodes that assumption. It suggests that water does not depend on narrow conditions to persist. It does not require sunlight, open skies, or even a planetary surface. Instead, water follows gravity, pressure, and time. Wherever ice, rock, and internal energy coexist, liquid water may emerge and remain, shielded from the chaos of space by layers of insulating material. This shift alters how rarity itself is defined. If habitable environments are measured only by Earth-like conditions, then they may indeed be scarce. But if habitability includes dark, sealed oceans beneath ice, the universe appears far more generous. Worlds once dismissed as frozen and lifeless become candidates for long-term stability. The question is no longer whether water is rare, but whether visible water is. Hidden oceans suggest a universe structured more like an iceberg than an island. What we see, planets with atmospheres, surfaces, and climates, may represent only a small fraction of what exists. Beneath that visible layer lies a much larger domain of concealed environments, operating quietly and persistently. These environments may not announce themselves through light or motion, but they may dominate the cosmic inventory of liquid water. This realization carries philosophical weight. It implies that existence does not need to be dramatic to be widespread. Oceans may fill the universe not as blue surfaces under stars, but as dark interiors sealed away from observation. If life arises in such places, it may do so frequently, yet remain largely invisible. The universe, in this view, may be rich in activity, but poor in spectacle. The concept of rarity is deeply tied to observation. Humans naturally value what can be seen, measured, and compared. Hidden oceans resist this impulse. They exist beyond direct experience, known only through inference and modeling. Their abundance challenges a worldview built around visibility, suggesting that what matters most may lie beyond immediate perception. This also reshapes the idea of significance. Earth's oceans are significant not only because they are visible, but because they shape climate, support life, and interact with the atmosphere. Hidden oceans perform similar roles within their own worlds, influencing internal dynamics and chemical evolution. Their significance is local rather than global, internal rather than outward-facing. They matter deeply to the systems they belong to, even if they leave little imprint beyond their boundaries. In this context, life itself may be less rare than previously thought, but also less communicative. If life thrives primarily in hidden oceans, it may not produce signals detectable across space. It may not alter atmospheres or emit radiation. It may remain silent, its existence woven into the internal fabric of its world rather than broadcast outward. This possibility reframes the long-standing question of cosmic loneliness. Silence may not imply emptiness. It may simply reflect concealment. Such a universe would be both abundant and solitary. Many worlds could host life, yet few would ever interact. Each ocean would be a closed system, evolving in isolation, shaped by internal conditions rather than cosmic exchange. The universe would not be a network of communicating civilizations, but a collection of self-contained ecosystems, each complete in itself. This perspective also softens the pressure to find confirmation. The value of hidden oceans does not depend on proof of life. Their existence alone expands the range of possible outcomes in planetary evolution. They demonstrate that water and energy can coexist in ways once considered unlikely. They reveal that stability can emerge without visibility, and that complexity can arise in darkness. For humanity, this realization invites a quieter form of curiosity. It encourages exploration motivated not by conquest or immediacy, but by understanding. The search for hidden oceans is not about finding mirrors of ourselves, but about recognizing diversity in how worlds can be structured. It is about accepting that some answers may remain indirect, inferred rather than observed. In practical terms, this shift influences scientific priorities. Missions are designed to detect subtle signals rather than dramatic features. Models emphasize long-term stability rather than short-lived habitability. The focus moves from surface appearances to internal processes. Understanding a world becomes an exercise in patience, requiring synthesis of small clues over extended periods. On a cultural level, hidden oceans resonate with broader human themes. They echo the idea that much of reality lies beneath the surface, whether in nature, history, or individual experience. They remind us that absence of evidence is not evidence of absence, and that significance does not require display. In a universe shaped by hidden processes, humility becomes a scientific virtue. As the documentary approaches its conclusion, the narrative begins to slow further, turning from expansion to reflection. The story of hidden oceans is not one of discovery completed, but of perspective transformed. It changes how water, life, and rarity are understood, replacing narrow definitions with broader possibilities. Oceans that do not need us. There is something quietly humbling about an ocean that exists without ever being seen. No shores are shaped by its waves. No skies are reflected on its surface. No history records its presence. These oceans do not respond to observers because they do not require them. They persist whether they are known or unknown, explored or ignored. In their silence, they challenge a deeply human tendency to measure importance by visibility and interaction. On Earth, oceans are inseparable from human history. They are routes of travel, sources of food, symbols in language and myth. They are mapped, named, and claimed. Even the most remote seas are tied into global systems of climate, commerce, and communication. Hidden oceans beneath ice belong to no such narrative. They exist beyond geography and beyond culture, shaped entirely by physical law rather than human meaning. This independence is part of their significance. It suggests that the universe is not structured around observers. Worlds do not wait to be discovered in order to matter. Processes unfold according to gravity, chemistry, and time, indifferent to whether they are ever understood. Hidden oceans embody this principle in its purest form. They are complete systems, sealed from the outside, sustained by internal balance rather than external exchange. If life exists within these oceans, it would share this independence. Such life would not evolve in response to distant stars or changing skies. It would not develop in dialogue with a larger cosmos. Its entire evolutionary history would unfold within the confines of its ocean, shaped by slow gradients and subtle shifts rather than dramatic events. From its perspective, the universe would be water, rock, and ice, nothing more, nothing less. This idea invites reflection on how context shapes meaning. Human understanding of the universe is built on contrasts, day and night, land and sea, surface and sky. hidden oceans erase many of these distinctions. There is no horizon, no weather, no external reference point. Reality becomes inward-facing, defined by what is present rather than what is absent. Existence narrows, but in doing so, it becomes self-sufficient. Such environments also redefine the concept of exploration. Much of exploration, historically, has involved movement across open spaces, crossing oceans, climbing mountains, traveling between planets. Hidden oceans cannot be approached in this way. They resist direct access. They require inference, patience, and restraint. To study them is not to traverse them, but to listen carefully for subtle signs of their presence. In this sense, hidden oceans align more closely with fields like geology or deep time than with traditional exploration narratives. Understanding comes not from arrival, but from accumulation of evidence. Each measurement, each model, adds a small piece to a picture that may never be complete. Knowledge grows asymptotically, approaching understanding without fully reaching it. There is a quiet discipline in this approach. It demands acceptance of uncertainty and comfort with incomplete answers. Hidden oceans remind scientists, and by extension, humanity, that not all questions yield definitive conclusions. Some environments can be known only partially, and that partial knowledge must still be valued. This perspective carries ethical implications as well. If these oceans are isolated and ancient, then intrusion becomes a serious consideration. The desire to know must be balanced against the responsibility to preserve. Introducing contamination into an environment that has evolved in isolation for billions of years would represent a permanent alteration. Respect, in this context, means recognizing limits. Even without direct contact, these oceans already influence human thought. They expand the imagination, offering new ways to think about life, stability, and abundance. They suggest that the universe may be more internally complex than outwardly expressive. Much of its richness may be hidden, folded inward, protected by layers that resist easy access. This realization subtly reshapes humanity's sense of place. Earth becomes one expression among many, not necessarily the template by which all worlds are judged. Its oceans are visible, dynamic, and interconnected with the sky. Other oceans may be dark, sealed, and entirely self-contained. Neither is more valid. They are simply different outcomes of the same physical laws. Hidden oceans also challenge narratives of destiny. They suggest that not all life, if it exists, is meant to spread, communicate, or be discovered. Some life may exist only to persist, completing its entire history within the boundaries of a single world. Meaning, in such cases, is internal rather than relational. Existence does not require an audience. Time beneath the ice. Time behaves differently in places untouched by light. On Earth's surface, time is marked by movement, sunrise and sunset, tides rising and falling, seasons advancing with predictable rhythm. Even in the deep ocean, far from sunlight, traces of this rhythm remain. Organic matter drifts downward in pulses. Currents respond, however faintly, to surface conditions. The passage of time is written into the environment through cycles and change. Beneath the ice of distant moons, time loses many of these markers. There are no days or nights, no seasons, no weather patterns to divide existence into intervals. Instead, time becomes continuous and smooth, unfolding without obvious punctuation. Change still occurs, but it does so quietly, measured in geological processes rather than visible events. In these hidden oceans, stability is the defining characteristic. Temperatures vary little. Pressure remains constant. Chemistry shifts slowly, guided by gradual reactions rather than sudden influxes of energy. An ocean beneath ice may persist in this state for hundreds of millions or even billions of years, changing only as its parent world slowly cools or its orbit subtly evolves. In such an environment, time is not experienced as a sequence of moments, but as an extended present. For any life that might exist there, this alters the nature of adaptation. On Earth, organisms respond to fluctuating environments. They evolve under pressure from changing conditions, competition, and disruption. Beneath ice, evolutionary pressure would be gentler but relentless. Survival would depend less on speed or flexibility and more on endurance. Life would adapt to constancy rather than change. This raises the possibility that some of the longest-lived ecosystems in the universe may be entirely hidden. While Earth's surface environments are dynamic and often unstable, subsurface oceans could offer continuity on a scale rarely achieved elsewhere. Once established, conditions might remain favorable for life far longer than on planets exposed to stellar variability, impacts, and atmospheric loss. Time also shapes chemistry in subtle ways. Slow reactions that would be insignificant over short periods become transformative when given millions of years. Molecules accumulate, structures form, gradients persist long enough to be exploited repeatedly. In this sense, time becomes a resource, compensating for the lack of energy and complexity. What cannot happen quickly may still happen eventually. There is a parallel here with Earth's geological record. Processes that seem imperceptible, continental drift, mountain building, erosion, reshape the planet given sufficient time. Beneath icy moons, similar patience governs everything. Oceans circulate slowly. Ice deforms gradually. Heat leaks outward at a measured pace. The world evolves, but so slowly that its present state appears timeless. From a human perspective, this challenges intuition. We often associate significance with change events, transitions, beginnings, and endings. Hidden oceans suggest that significance can also arise from persistence. A system that remains stable for billions of years is no less remarkable than one that changes rapidly. In fact, such endurance may be rarer. Time beneath the ice also invites reflection on humanity's own temporal scale. Civilizations rise and fall in thousands of years. Species evolve in millions. Planets change over billions. Hidden oceans operate at the outer limits of this scale, reminding us that much of the universe unfolds at a pace far removed from human experience. To understand it requires patience, not just technologically, but conceptually. As exploration continues, scientists must adapt to this reality. Missions last decades. Models extend across geological time. Evidence accumulates slowly. Progress is incremental, and certainty remains elusive. Yet, within this slow unfolding, understanding deepens. Each insight builds on the last, forming a quiet narrative that mirrors the environments being studied. Hidden oceans, shaped by time rather than light, stand as reminders that the universe is not hurried. It does not rush toward outcomes or conclusions. It allows processes to play out fully, regardless of whether they are ever observed. In acknowledging this, humanity gains a broader sense of perspective, one that values patience, depth, and continuity over immediacy. A quiet, closing reflection. Imagine a frozen moon, suspended in darkness, orbiting silently around a distant planet. From the outside, it appears unchanged, a pale surface etched with faint lines and shadows. There is no movement visible, no indication of activity, and yet, beneath that still exterior, an ocean may be slowly circulating, vast, dark, and enduring. This documentary has been a descent into that unseen world, not a descent measured in distance, but in layers of understanding. Ice gave way to water, water gave way to chemistry. Chemistry opened the possibility of life. Along the way, familiar assumptions were gently set aside, replaced by a broader view of what oceans, habitability, and existence can mean. Hidden oceans do not resemble the seas that shaped human history. They do not invite navigation or reflection under open skies. They do not sparkle or surge. Their significance lies not in spectacle, but in persistence. They exist because physical laws allow them to exist, sustained by gravity, pressure, and time, that alone is enough. Whether or not life has arisen within them remains an open question. But even unanswered, the question itself changes how the universe is perceived. It suggests that water so central to life as we know it may be abundant in forms that resist observation. It hints that the universe's most important environments may not be those we see first, but those hidden beneath surfaces, waiting patiently. In this sense, icy moons become symbols rather than destinations. They represent the idea that reality extends inward as well as outward, that depth matters as much as distance. That silence does not imply absence. Beneath frozen surfaces, processes unfold that are no less real for being unseen. As humanity continues to explore, these worlds will remain just beyond reach for some time. Their oceans will continue to circulate without witness. Their chemistry will continue to evolve. If life exists there, it will persist in its own way, unaware of the distant stars or the questions being asked light years away. And perhaps that is the quiet lesson of hidden oceans, that existence does not require recognition, that the universe is not arranged for observation, but for balance, that vast systems can thrive in darkness, shaped by patience rather than light. Somewhere beneath ice, far from the warmth of any sun, an ocean may be moving slowly, unchanged by our curiosity, enduring simply because it can. The depth that remains. There is a particular stillness that comes from knowing something exists beyond reach. Not lost, not destroyed, not waiting to be found, but simply present, continuing without interruption. The hidden oceans of icy moons occupy this kind of stillness. They do not resolve into answers. They do not conclude a story. They remain, quietly, as part of the universe's deeper structure. Throughout this journey, we have moved away from surfaces and toward interiors, away from light and toward pressure, away from immediacy and toward time. Each step has revealed that what feels empty from a distance can be full beneath inspection, and that what appears frozen may be quietly active. The lesson repeats itself across scale and context. Reality does not end where visibility does. These oceans do not resemble the environments humans evolved to understand. They offer no horizons, no skies, no cycles that mirror our days or seasons. They are enclosed, insulated, and patient. Their motion is slow. Their chemistry is subtle. Their history unfolds without punctuation. And yet, they are among the most stable environments known, capable of persisting while surface worlds change beyond recognition. In this stability, there is a kind of permanence rarely found elsewhere. Stars burn out, atmospheres escape, planets fracture and collide. But beneath ice, water may remain liquid long after surface conditions become hostile. The universe, it seems, has many ways of preserving what matters, even when everything else changes. It is tempting to frame these oceans in terms of discovery, what they might contain, what they might reveal, what they might mean for humanity. But they resist that framing. Their significance does not depend on outcome. Whether they host life or remain purely chemical systems, their existence alone reshapes understanding. They demonstrate that the universe supports complexity in forms that do not announce themselves. This realization subtly alters how questions are asked. Instead of searching only for places that resemble Earth, attention shifts toward processes that allow persistence. Instead of prioritizing visibility, value is placed on endurance. Instead of assuming that life must be dramatic to be meaningful, the possibility emerges that life, if it exists, may be quiet, slow, and almost indistinguishable from its environment. Hidden oceans also reveal something about human curiosity. The desire to understand them is not driven by urgency or utility, but by recognition. Recognition that the universe is deeper than it appears. Recognition that many of its most important systems operate beyond immediate perception. In seeking these oceans, humanity practices a form of curiosity that accepts limits and values patience. There is a parallel here with inner worlds as well as outer ones. Just as planets have depths that cannot be seen from orbit, understanding often requires moving beyond surfaces. Beneath appearances lie processes that shape outcomes quietly and persistently. The study of hidden oceans becomes a metaphor as much as a scientific endeavor, a reminder that depth matters. As technology advances, fragments of these worlds will become clearer. Measurements will sharpen, models will refine. Some questions will narrow, others will open. But even with progress, these oceans will retain an element of mystery. They will never become fully familiar, and perhaps that is appropriate. Not everything in the universe is meant to be fully known. Still water, endless night. At the far edges of the solar system, where sunlight weakens into something almost symbolic, there are worlds that seem finished before they begin. Frozen surfaces, silent orbits, no atmosphere moving above them, no visible signs of change. From a distance, they appear complete, locked in a permanent state, untouched by drama or urgency. And yet, beneath that stillness, something may continue quietly, unchanged by how it appears from the outside. Hidden oceans do not announce themselves. They do not demand attention. They exist because conditions allow them to exist, and that is enough. Their presence is not dramatic, but it is profound. It suggests that the universe is capable of sustaining complexity without spectacle, of preserving motion without visibility, of holding depth beneath apparent simplicity. Throughout this journey, we have moved steadily inward, from frozen surfaces to living ice, from ice to water, from water to chemistry, from chemistry to the possibility of life. At no point did the universe require light to justify itself. At no point did it rely on familiarity. Instead, it followed rules, pressure, gravity, heat, time, and allowed outcomes to unfold quietly, without concern for whether they would ever be seen. This perspective alters the meaning of exploration. Exploration is often imagined as arrival, reaching a destination, crossing a boundary, making contact. But the hidden oceans resist arrival. They remain sealed, insulated, patient. To explore them is to accept distance, to work with inference rather than presence, and to build understanding without expectation of closure. In this way, they teach a slower, more restrained form of curiosity. They also soften the urgency of answers. The question of life beneath ice is important, but it is not the only measure of significance. Even without biology, these oceans reshape planetary evolution. They redistribute heat, they alter internal structures, they influence surface features and orbital behavior. They are active participants in their world's histories, even if they leave no obvious trace beyond their boundaries. If life does exist within them, it would exist without witnesses. It would not evolve toward visibility or communication. It would persist because conditions permit persistence. Its story would be complete within itself, unfolding across time spans that dwarf human history. Such life would not need to be discovered to be meaningful. It would simply be. This idea runs counter to a deeply human instinct, the belief that significance requires recognition. Hidden oceans challenge that instinct gently but firmly. They suggest that the universe is not organized around observers. It does not arrange itself to be understood. Much of what exists does so independently of whether it is ever noticed. There is a quiet comfort in this realization. It implies that existence is stable, not fragile, that complexity does not require constant attention, that systems can endure without validation. In a universe shaped by such principles, humanity becomes part of a larger pattern rather than an exception to it. The comparison to Earth remains unavoidable. Our own oceans, though visible, contain depths that remain largely unexplored. Vast regions of the seafloor have never been seen directly. Life persists there, in forms still poorly understood. Even on our own planet, much of reality operates beyond direct experience. Hidden oceans beyond Earth extend this truth outward, scaling it to planetary proportions. They also remind us that knowledge often arrives indirectly. Rarely does understanding come all at once. Instead, it accumulates slowly, built from subtle measurements, careful models, and patient interpretation. The story of icy moons is still being written, not through sudden revelation, but through gradual refinement. Each mission adds detail. Each observation narrows uncertainty. The process mirrors the environments being studied: slow, deliberate, and resilient. Somewhere, beneath ice thick enough to block every trace of light, water may be moving, slowly, patiently, unaware of stars or observers, shaped only by gravity, chemistry, and time. That motion may continue long after surface worlds change, long after questions are asked and forgotten. An ocean that continues. Even after everything that can be said, the most accurate description of a hidden ocean is simple. It continues. It does not accelerate toward discovery. It does not pause for observation. It does not respond to curiosity or expectation. Beneath ice that has never cracked open to a sky, water moves slowly, shaped by weight and warmth, guided by gradients so subtle they would escape notice in any other context. This continuation is not dramatic, but it is profound. It represents one of the universe's most enduring patterns, systems that persist quietly, governed not by attention, but by balance. Throughout this documentary, the descent has been inward rather than outward. Each chapter has moved deeper into environments where familiar reference points fade away. Light disappears. Motion slows. Time stretches. In doing so, the story has gradually loosened its connection to spectacle and tightened its connection to fundamentals. Pressure, chemistry, energy, duration. These are the forces that shape hidden oceans, and they are the same forces that shape much of the universe beyond immediate perception. What makes these oceans remarkable is not that they might host life, though that possibility remains compelling. It is that they demonstrate how much of reality operates independently of surface conditions. Planets lose atmospheres, stars brighten and dim, orbits shift, yet beneath layers of ice, water may remain liquid through all of it, insulated from volatility by depth itself. The universe, it seems, has learned how to protect complexity by hiding it. This idea reframes how stability is understood. On Earth, stability is often associated with moderation, temperate climates, gentle cycles, and balanced ecosystems. In hidden oceans, stability emerges from extremes. Immense pressure prevents boiling. Thick ice prevents freezing. Isolation prevents disruption. What appears hostile becomes protective. What appears limiting becomes sustaining. Such environments challenge human intuition because they invert familiar relationships. Light is no longer essential. Visibility is no longer correlated with importance. Change is no longer rapid or obvious. Instead, significance accumulates through duration. A process that unfolds over billions of years acquires weight simply by continuing to unfold. In this sense, time itself becomes the dominant resource. The idea that oceans may exist without ever being seen carries a quiet philosophical weight. It suggests that existence does not need to justify itself through interaction. A system does not need to influence others to be complete. It does not need to be discovered to be real. Hidden oceans remind us that much of the universe operates in this way, self-contained, internally consistent, and indifferent to observation. For humanity, this realization subtly reshapes the role of exploration. Exploration becomes less about reaching and more about understanding, less about arrival and more about inference. The study of hidden oceans relies on patience, modeling, and restraint. It accepts that some environments may never be directly accessed, and that indirect knowledge can still be meaningful. This approach mirrors the scientific process itself. Many of the most important discoveries in science have come not from direct observation, but from careful interpretation of subtle effects. Gravity was understood long before it could be measured directly. Atomic structure was inferred before it was seen. Hidden oceans belong to this tradition. They are known through influence rather than presence, through consistency rather than spectacle. There is also a quiet ethical dimension to this understanding. If these oceans are isolated and ancient, then restraint becomes a form of respect. Not every environment needs to be entered to be understood. Not every mystery needs to be resolved to be meaningful. Sometimes, recognizing the existence of something and allowing it to continue untouched is itself a form of wisdom. This perspective does not diminish curiosity. It refines it. Curiosity becomes slower, more deliberate, less urgent. It values coherence over completion. In a universe where some of the most enduring systems are hidden, curiosity learns to coexist with uncertainty rather than eliminate it. Hidden oceans also invite a re-evaluation of scale. On human timescales, they are static. On geological timescales, they are active. On cosmic timescales, they may be among the most persistent environments known. They occupy a middle ground where change is constant but imperceptible, where motion exists without disturbance. This scale mismatch reminds us that perception is not a reliable guide to importance. As the universe ages, stars will exhaust their fuel, surface worlds will cool, radiation will fade. Yet subsurface oceans, protected by depth and pressure, may endure long after surface habitability ends. In this distant future, life, if it exists, may retreat inward rather than outward. The last refuges of complexity may not be planets with skies, but worlds sealed beneath ice. In this way, hidden oceans become not just a feature of the present universe, but a hint of its future. They suggest that as energy becomes scarcer and conditions become harsher, stability will favor environments that minimize exposure. Depth will replace surface. Insulation will replace atmosphere. Persistence will replace expansion. This idea carries a quiet symmetry. Life may begin at surfaces, driven by abundance and light, but endure in depths, sustained by patience and efficiency. The universe may open with spectacle and close with silence. Not empty silence, but the silence of systems that continue without announcement. That continuation does not need interpretation to be meaningful. It stands as evidence that the universe is not shallow, even where it appears still. That depth exists where surfaces suggest finality. That oceans quiet, dark, and unseen may be among the most common expressions of stability in all of space. Depth held. There is a point at which explanation gives way to acceptance, not because understanding has failed, but because it has reached a natural stillness. The idea of hidden oceans does not demand a final interpretation. It asks only to be held quietly, without urgency, much like the environments it describes. Across this journey, familiar anchors have gradually loosened. Light receded. Surfaces lost their authority. Motion slowed until it became almost indistinguishable from rest. What remained were fundamentals: water under pressure, heat moving gently, chemistry unfolding at a patient pace. These are not dramatic ingredients, but they are sufficient. Given time, they are powerful. Hidden oceans remind us that the universe does not rely on exposure to sustain complexity. It does not require open skies or visible motion. It allows systems to form inwardly, protected by depth and insulation. In doing so, it creates environments where change is not absent, but restrained, where persistence becomes the dominant feature. This inward turn carries a subtle lesson. Much of what matters may be inaccessible by design, not because it is forbidden, but because it is stabilized by separation. Depth protects, isolation preserves. Ice becomes not a barrier, but a guardian. In these worlds, concealment is not failure, it is function. Human curiosity often moves outward, seeking distant horizons and visible markers. Hidden oceans suggest an alternate direction, one that moves inward, toward layers and processes that do not announce themselves. They invite a curiosity that listens rather than arrives, that infers rather than claims, that is content with partial understanding. There is a certain quiet dignity in environments that do not change in response to attention. They do not become more real when observed. They do not become meaningful when named. Their reality is self-sustaining. In this way, hidden oceans mirror much of the universe itself, vast, indifferent, and steady. If life exists within these oceans, it would share this dignity. It would not evolve to be seen. It would not adapt to recognition. It would persist because persistence is possible. Its story would be written in chemistry and time, not in signals or monuments. Such life would not be lesser for its silence. It would simply be different. Even if life never arises, the oceans remain significant. They are reservoirs of stability in a changing universe. They are evidence that water, one of the universe's most transformative substances, finds ways to endure. They are reminders that what appears frozen may be actively balanced beneath the surface. As the universe ages, these hidden systems may become increasingly important. Surface environments are vulnerable. Atmospheres escape. Stars evolve. Radiation intensifies or fades. Depth, by contrast, moderates extremes. It preserves conditions long after exposure becomes untenable. The future of complexity may belong not to open worlds, but to enclosed ones. This possibility reframes long-held narratives about progress and expansion. It suggests that endurance may ultimately favor restraint, that survival may move inward rather than outward, that the last oceans may be those no one ever sees. In reflecting on hidden oceans, the mind naturally slows. There is no urgency here, no call to action, no resolution to chase. The idea settles instead, becoming part of a larger understanding of how the universe organizes itself. It is an understanding that values balance over brilliance, patience over speed, and depth over display. And so, the image returns once more, not as a conclusion, but as a resting point. A frozen moon, pale against the dark. Beneath it, an ocean moving slowly, guided by forces older than stars. No light reaches it. No witness marks its passing. It continues because the conditions allow it to continue. What stays with us, in the end, is not an image, but a sense of depth. The hidden oceans of icy moons do not resolve into certainty. They do not offer a final answer about life, or a clear boundary between the living and the lifeless. Instead, they leave behind a quieter understanding that the universe is shaped as much by what is concealed as by what is visible. That beneath surfaces which appear finished, processes may continue patiently, unchanged by attention or absence. These oceans remind us that water does not need skies, and that motion does not need light. They show that stability can arise from pressure, that endurance can emerge from isolation, and that complexity can persist without ever announcing itself. In doing so, they gently expand the idea of what a world can be. Perhaps the most enduring insight is this: much of reality does not exist for observation. It exists because physical laws allow it to exist. Oceans beneath ice, sealed for billions of years, moving slowly in darkness, are not waiting to be discovered in order to matter. They are complete in themselves. As the universe continues to age, surfaces will change, stars will shift, worlds will cool and erode. Yet somewhere beneath frozen shells, water may remain liquid, balanced and contained, carrying forward a quiet continuity. Not dramatic, not fragile, simply persistent. And so, we leave these hidden oceans where they have always been, beneath the ice, beyond the light, shaped by gravity and time, unseen, untouched, and ongoing. The depth remains.